Alright, good afternoon, everybody. We are here for our second lesson in acids and bases. And we're going to talk a little bit today about pH and about indicators and what those things are. As you can see here, we're starting off by looking at the pH scale. Yesterday we talked about what it meant to be an acid and what it meant to be a base. Talking about the fact that if something is an acid, it either produces or gives H pluses, and if it is a base, it produces OH or accepts the H plus. Now, I seem to have lost... Oh, no, I haven't. Okay, cool. If we have something that is an acid, it's something that has H plus either to give or not to give. No, not to give. It has H plus to give to other things. H plus. And something that has a base has two options. It either has OH minus or takes H plus. And we saw some of that yesterday. I'm cutting in and out. That's not great. Hold on. Move close to the mic. Alright. Let's try that then. When we're talking about pH, we're talking about measuring an acid and measuring a base and seeing how acidic or how basic something is. Right? When we have an acid has a pH below 7, right? So all these things down here are acidic, and a base, acidic, and a base, all these things above 7 are basic. When we are measuring how acidic or how basic something is, we can have NaOH that is a pH of 8 or 9 or 10 or 11 or 12 or 13 or 14. Right. The identity of the base doesn't tell you its pH. It's based on the concentration of H plus that is present, which is measured by this fancy logarithmic equation that we're not going to use. Right. This is 4AP. When we have pH that we want to measure, we're going to do it by measuring the concentration of the H plus in a much more, not much more, in a much less complicated way. Bases take H plus, basically, if they are, so I don't have the ability to erase my writing anymore, which is annoying. That's not doing it. That's not doing it. Oh, it works now. Nice. Cool. So, give me 1 second and I can erase my writing here and we can talk about all the rest of this. Alright, sorry. So, do we generally need to know the equation for the regions? No. This is, again, not for us. This is for AP. We don't need to know this equation. We're going to use this shortcut. And the shortcut is going to be able to answer all of our questions. So, pH is a way to measure how acidic or how basic something is, right? Every acid, every base falls on this scale. If it's less than 7, the closer it gets to 0, the more acidic it is. The higher up, right, the closer to 14, the more basic it is. And when we're looking at pH, we're looking at the concentration of H+. It's a measure of how acidic it is. If we have something that has a concentration right? Let's say we have HCl with a concentration of 0.1 mole. Is the shortcut something you need to know how to solve, or is it something you'll just need to memorize? You'll just need to know how to use it. Not necessarily a memorization. As we do more and more problems, we'll see kind of how this plays into it. It looks like a much more complicated formula than it is, but I'm going to show you in a second. Right? If I want to know the pH of this thing, right? If I want to know how acidic or how basic this thing is, I'm going to put this into scientific notation. So that's 1 times 10 to the negative 1. The shortcut is not on the reference table. I would put this, right, concentration into scientific notation. The pH of a substance is then going to be this number. Right, so this has a pH of 1. The more concentrated, right, the more concentrated our substance is, the lower the pH is going to be for an acid or for an acid. Right. So if I have, let's say I have HCl with a concentration of 0.01. Get erased. Thank you. If I have HCl with a concentration of 0.01. Now when I put this into scientific notation, it's 1 times 10 to the negative 2, which means my pH is 2. So when we're looking at pH, it works on a scale of hundreds. If I have something with a pH of 2, or sorry, it works on a factor of 10, not hundreds. It works on a factor of 10. If I look at something with a pH of 1 compared to something with a pH of 2, it's not a single step. It's actually 10 times more acidic or 10 times more basic. And I'm going to pull up a way to show us that right now. This is way more difficult than it was yesterday. I'm going to leave those there. All right, so if I have two things, let's say I have HCl at a concentration of 0.001, and then I have HCl at a concentration of 0.01, and HCl at a concentration of 0.1. If I want to find the pH of these things, if the... Oh, sorry, pause for a question. Pause. Okay, so this H3O plus in the brackets is a synonym for H plus concentration. Right, so they're synonyms for each other. There was another question. What if the exponent is positive? Then you have a negative pH, which is possible. The more concentrated an acid is, the lower the pH. The more concentrated a base is, the higher the pH. So they get further away from neutral, which is our distilled water, or just plain H2O example. So if we're looking at these three things, and I want to compare the pHs of these three things, right? HCl at 0.001 molarity, HCl at 0.01 molarity, and HCl at 0.1 molarity. This doesn't help me right now. I need these to be into scientific notation. Right? When I put this into scientific notation, it's 1 times 10 to the negative 3, 1 times 10 to the negative 2, and 1 times 10 to the negative 1. Molarity. the pH is the value of this exponent. So this has a pH. This has a pH of 3. Nope, I didn't want to erase my 3. This has a pH of 3. This has a pH of 2. This has a pH of 1. Right. And when we compare these things, right, this is just a step of 1 pH, right? It went down by 1 pH, but it is 10 times more concentrated. Right? This went down a pH of 1, but it's 10 times more concentrated. So something that's really important is that each step on the pH scale is a change of 10 times concentration. So if we have something that goes from, if we're comparing a 5 to a 2, right? If I want to compare a pH of 5 to a pH of 2, it's 10, 100, 1,000 times more acidic. Right? Right, that's 1,000 times more acidic because each step is a factor of 10. Right? The big M is molarity, right? It's a measure of concentration, like we talked about in our previous units. If the exponent is positive, you have a negative pH, which is possible, but not something that we will see a lot of. H plus concentration is just the concentration. We use that to then determine the pH. The exponent is the number of decimal spots. It's scientific notation. So if I want to put this number into scientific notation, I have to move the decimal 3 times. All right, so something with 1 times 10 to the negative 4th has a pH of 4, correct. It can be a decimal, right? You can have a pH of 4.6 or 5.2. We are not going to see that. That's where this comes in. This formula, this AP level formula. But again, because it's just for AP and not really for us, we're going to see whole number pHs, and that's it. Is there a reason why we can't eat anything that's basic, but we can eat most things that are acidic? You can eat basic things. Chocolate is basic. If you ever have like Tums are basic. So it's just there's more acidic things that we eat than basic things that we eat. Right. Can I implement how to do the shortcut again? Yes. So, actually, yes. I'm going to do that here, though. What is the pH of the following solution? With something that has a concentration of, right, again, this is telling you the concentration. We know that the concentration is 1 times 10 to the negative 6th. We know the shortcut is 1 times 10 to the negative pH. So this is going to be our pH, which means this is going to be our pH. It doesn't matter that it's a negative 6, right? Our pH is 6. Right, so our molarity should be given to us. Right, our molarity should be given to us. They're going to tell you, right, I think I have another one. Hold on. All right, they're going to give you concentration, they're going to give you molarity, and it's your job to then change it into scientific notation. And then remember that this number is your pH. right? So you're not going to have to solve an equation for H plus concentration. You're just going to have to change numbers from scientific notation in and out of scientific notation. Right? So, putting this into scientific notation, 1 times 10 to the negative 3, because I had to move the decimal 1, 2, 3 spots, making 1 times 10 to the negative 3 molarity, making my pH 3. Right, nicely done. The charge should be negative because, again, we're looking at things that are stuck on the pH scale from 0 to 14. So we're always going to have something that has a pH that is negative. Sorry, not a pH that is negative, sorry, but an exponent that is negative. Because if we have an exponent that's negative, then our pH is positive. If you end up with a positive number up here, you have something that is either very, very, very acidic or very, very, very basic. Right? It's not that the charge negates. Anything can have a negative pH if it's a strong enough acid. It's just that most things fall from 0 to 14. So I can have, let's say I had 10 molar HNO3. Alright, that's 1 times 10 to the positive 2. Right, and if I want to figure out how to make this into a pH, that would be 1 times 10 to the negative pH. If this is going to be equal, then my pH is going to be negative 2. Right. Are you going to have to solve for the H plus concentration? Yes, but not yet. That's something we're going to talk about tomorrow, is the kind of problems that you're going to have to solve them through to solve for the H plus concentration. All right, so why is it negative 2? 1 times 10 to the positive 2. If this is equal to this, positive 2 equals negative pH, negative 2 is going to equal positive 2, so we're going to have a pH of negative 2. Again, not something we're going to see because we're focusing on things that have a pH between 0 and 14, but it is possible, right? Because people are asking, is it possible to be outside of that scale? It is very possible to be outside of that scale. So if it said, what is a pH of a 10 molar? Exactly, Cayenne. Right? We will never have a problem with a positive exponent. It will always be negative because we don't want anything too acidic. Right? Ooh, Willa, I love that question. And I'm going to refresh this slide so that we can answer it. Easiest way to clear all my ink. Good. So, Willa says if it has a concentration of 0.1, 2, 3, 4, 5, 6, 7, 8, 9, 1 molarity H plus, which is 1 times 10 to the negative 10 molarity of H plus, that would be a pH of 10. So yes, that would be a base. Right? When we look at pH and we look at whether something is acidic or basic, it's when we look at something that's whether it's acidic or basic, when we're looking at pH, we're looking at like a sliding scale. It's how much H plus is there, and it's either a large amount, so it's acidic, or on the other side of the scale, it's very little H plus, so it's basic. And that's where we go from 0 to 14 with 7 in the middle. Right? We're not going to have a problem with pH of over 14. We're not going to have a problem with pH of less than 0, but those are things that are possible. Right? When we have water in the middle, it's not that there's lots of H plus or very little H plus. There's an exact middle amount of H plus. Right? When we look at water, it's exactly even H plus and OH minus. Right? Because we can talk about them in the opposite. Right? We can talk about lots of H plus or very little. That's not how you spell very. Very little OH minus. Water is in the middle. Water is our neutral pH because it's exactly in the middle. It's not lots of H plus and very little OH minus. It's not lots of OH minus and very little H plus. It's exactly equal H plus and OH minus. Right? Water is both acidic and basic. Right? It's equal parts acidic and basic, which is why it's right in the middle. If you get more acidic than water, you go towards the 0. If you get more basic than water, you go towards the 14. But water, exactly 50-50, acid and base, right? Exactly halfway between the two is going to be our neutral point. So it must be distilled water. It should be distilled water because we don't want anything else in the water. If we have like salt water is a little bit more basic, not a lot, but a little bit more basic just because of the salt added to it, for reasons that we'll see a little bit later on. Right. So when we're talking about water being neutral, that's distilled water being neutral. Can I explain Willa's question again? So Willa asked about this situation, an acid, right, with this concentration of H+. So it's a very, very weak acid. It's actually such a weak acid that it has a pH of 10. It has such little H+ that it's actually over here on the 10 side. Right? Because when we're doing concentration, right, when we're looking at these things for pH, we're looking at taking those numbers and putting them into scientific notation, and then taking the exponent, and that will be our pH. Right? So here, this is our pH. It's a pain in the butt to constantly measure concentrations of things, though. And so what we have for us, what we have to use is, whoa, hey, what happened there? There we go. What we have to use are indicators. And indicators are going to tell us the pH of a substance through color change. Right? They're color sensitive. And because of this color sensitivity, we can use them to look at, right, we can put them in an acid or put them in a base, and it will give us a vague idea of what the pH is of that thing. Nicole, in an acid-base mixture with a 1-to-1 ratio, does it have to be evenly combined to be neutral? If it's a 1-to-1 ratio, it is evenly combined. But that would neutralize it, yes, which is what we're going to talk about tomorrow. Right. So indicators are these cool. I wish I had a full whiteboard and could actually stand in front of you to do this out, but indicators are color sensitive. They change color depending on the pH of the solution that you put them in. So you can have it be, red in one solution, and then it'll change to blue in another solution based on the pH. And it'll go back and forth, and I know, well, if it's blue, that means it's a base, and if it's red, that means I know it's an acid. And we have a whole piece of our reference table that we actually get to look at and use in order to see what the indicators are going to tell us. And that table is table M. Whoop, too far. And that table is table M. I'm going to take a second here and pull up an actual copy of table M, because I know that everyone has it in front of them at all times. And so I'm going to pull that up for us as well. Alright, table M on your reference table looks very different from what you see on the slide right now in front of you. Alright, your table M looks like this. Your table M looks like this. Now, table M tells you everything that my colorful slide tells you. It just tells you to it without it being in color. Each of these things is an indicator, right? Each of these things on my list, right? Methyl orange, bromthymol blue, phenolphthalein, litmus, bromcresol green, and thymol blue, right? These 1, 2, 3, 4, 5, 6 things are indicators. They change color based on the pH range that you put them in. And we'll see. I'm going to try to adjust just a little bit here. Right, we're going to focus on methyl orange right now. All right, methyl orange is our first row up here. Right, you see that it's either red, orange, or yellow. Right. Methyl orange will either be red, orange, or yellow. And it will change colors based on the pH. So if you have methyl orange in a pH below 3.1, right, methyl orange in a pH of below 3.1, it will be red. Right, so pH of 1, methyl orange is red. pH of 2, methyl orange is red. pH of 3, methyl orange is red. pH of 3.5, pH of 4, right, something in this range, it will be a mix of red and yellow. It will be the mixture, the combination of the two. It would be orange. pH of 4.5, pH of 5, 6, 7, everything higher than a pH of 4.4 will make methyl orange turn yellow. And that's how this whole table works. Right? If I wanted to look at bromthymol blue, and I wanted to slide down, would you please slide down for me? That would be super nice. There we go. If I look at bromthymol blue, it changes color between 6 and 7.6. Everything below a pH of 6, it is yellow. Everything above 7.6, it is blue. Everything between 6 and 7.6, it will be a combination of yellow and blue, so it will be green. Right, so if you have something with a pH of 5 and you want to test it, methyl orange would be yellow, bromthymol blue would be yellow, litmus would be purple. Right? So now, a couple of questions reading from the chat here. There are multiple yellow to blues, right? There are bromthymol blue and bromcresol green. They turn yellow to blue, but they do so at different ranges, right? So bromcresol green changes to blue a lot faster than bromthymol blue. So they each have their own uses. Hold up. Scrolling back up in the chat. How do you tell the difference between the two blues? You don't. The indicator can just tell you, right? Say I have something that's a pH of 12. All three of these things all four of these things are going to tell me that it's blue. Right? They're going to tell me it's a pH above 7.6. It'll tell me it's a pH above 4.9, 4.8. It'll tell me it's a pH above 8.5. Right? It just helps narrow it down. And we're going to do a practice problem in a second that I kind of help show what that is going to look like. Would it only change color in the presence of an acid? It would. Yeah, okay. So Georgia answered her own question. Indicators are going to change color if you have an acid, right? Let's say you have a really strong acid and you slowly add base to it. It would slowly change this color. It's from red to orange to yellow. The indicators, for the most part, are colorless liquids. Some of them are the colors that they say, right? I think bromthymol blue is a blue naturally. Bromcresol green, I think, is green naturally. Thymol blue, I think, is also blue naturally. Methyl orange, I'm pretty sure, is red. But they're liquid solutions that you make. It's only for the use of testing. And they're not particularly exciting. They look like food coloring. Phenolphthalein is clear. So that's the least exciting of the bunch. And yes, some of them are on pieces of paper, right? Some of them are like strips that you can test with, right? So if you've used litmus paper in living environment, right, you've seen that before. What do we call a mix of colorless and pink? Light pink, exactly. Phenolphthalein is the one that has no real mix, right? You can't call something like translucent pink. It's just a very light pink, and it gets deeper and deeper and deeper as you go closer to 14. What's the indicator color between colorless and pink? Right, it's a light pink, so it's colorless, light pink, and then pink. And then the rest of them are pretty straightforward, right? Red, orange, yellow, yellow, green, blue, red, purple, blue, yellow, green, blue, yellow, green, blue. This section here is true, right? That's like a statement of fact. But if you go back and look at the actual reference table, it doesn't show up on the reference table for thymol blue, just to try to avoid complicating things, right? Thymol blue, they only point out this transition between yellow and blue. They kind of ignore the red bit here, just for simplicity's sake. So, when they ask us questions, which 0.1 solution will turn phenolphthalein pink? If we look at... Tell me I just closed it. Yep. If we look at table M, which I now have to pull back up, right, we want to focus on phenolphthalein, and we want to focus on turning it pink. Right, so let's do that. Right. We have phenolphthalein, and we want it to turn pink, so that means we want a pH above 9. We want a pH above 9. Which means we want something that is basic. So when we look at these things, we want to be able to pick out the one that is a base. Right? Things that start with H are acids. So that's not going to be our answer. Right? CO2 is neither acidic nor basic, right? It has no H plus and no OH minus. LiOH has our OH minus, so that makes it a base. But then if we look at 4 also has an OH. When we're identifying bases, right, and this is something that's important, something that starts with a C, right, something that starts with a C is never a base. Something that starts with a C and has OH is an alcohol. Right, and I'm going to actually write that somewhere where it's not overlapping. Right, it's either an alcohol or acetic acid, which you can see on our reference table as well. If we scroll up to right, table K, which has our list of common acids, right, we have starts with an H, 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 starts with an H. Right? And then we have CH3COOH, right? That's our acetic acid, but they often write it where it starts with C, or sorry, it starts with an H. Our bases have OHs in them, or they are ammonia, but it's never going to be starting with a C with an OH is never a base. Right, so our answer here, we're looking for the base, and it's this LiOH as our answer. Choice 2 is carbonic acid. It needs to be a base because it needs to turn phenolphthalein pink, which means pH greater than 9, which is basic. Okay, pausing for questions here. It needs to be a base, right? Because they're asking us turning phenolphthalein pink, which table M tells us that it needs a pH greater than 9. We know that a pH greater than 9 is basic, so we're looking for the one of these that's a base. Right? Starting with an H, that's an acid. Aqueous CO2, that's an acid. LiOH, that's a base. And CH3OH, right, starts with a C, has an OH. It's an alcohol, not a base. We do ignore the red for thymol blue. If the pH is 8 or 6, will they determine whether it is a base or an acid or neutral? 8 is basic, 6 is acidic. The only neutral thing is 7. Will the question always be how to change to the extreme colors? No. They can definitely ask you about something on the in-betweens. Right? They can say which of the following right here. Let me actually just write one out for us. Right, this is going to be the last thing before I transition over to tutoring hours. Right, so if we look at a question, it could say something along the lines of, oh no, I would like to write, please. Boo. That is unfortunate, because I would very much like to write for us right now. Right, they can say something that says, which of the following pHs And they'll give you, you know, that's not how numbers work. All right, 1, 2, 3, 4 will be your choices, and they'll give you 14, 1, 6, 3.5. So if I'm looking here, right, which of the following pH values would turn methyl orange orange? I need the reference table. I need to flip over to methyl orange. I'm looking for a range where it's between 3.1 and 4.4. So it's not 1, it's not 2, it's not 3, it's gotta be choice 4. Right, so it can still ask you about the ranges. It can ask you about anything that falls into any of the information on this table. Right, it can ask you to do anything involving this table at all. Right, so whether that's asking you about, you know, something between 8 and 9, which would be a light pink for phenolphthalein, red litmus is red, litmus is red in acids and blue in bases, right? Anything on this table, any of these color ranges, any of the color changes, any of the in-betweens, all of that is fair game. Right? Something with a pH of 7.000001 is still considered a base. It would be a very, very weak base. So the red in thymol blue is going to be ignored, right? That's on the slide because it was a really good picture, right? Like, I couldn't find a better picture than this. But this part of the color changes isn't really going to be mentioned. A color change for litmus would be more of a purple, right? In the in-between here, right? In between red and blue, that's a purple. This would be an orange, a green, a light pink, a purple, a green, and a green. And again, we would ignore this part, the red part of the thymol blue. There's no light red for litmuses, right? They're going to just say red, purple, or blue. There's no, like, they're not going to say, like, what gives it the deepest yellow or the most vibrant red. They're not going to do that. But that being said, that is our lesson for today with pH calculations, looking at pH and table M. We'll come back tomorrow to talk about neutralization and walk our way through some practice problems for that. Right? I'm going to, again, transition us into office hours. If you have any questions, you want to do any practice problems, you can just stick around, and I'll transition us over to a new stream in about 2-3 minutes. All right? Have a great day.